All right, so I would go. All right, the question you're gonna tell me why I'm talking about total graph and trace graph uh, of a ring. I mean, what's the connection? You're gonna see that in a minute. So let's get to it. Here is the definition. You let A to be a commutative ring with non-zero identity, and you take N to be bigger or equal 1 less than infinity. And you take R, the product of these rings, well, the product of A, N times. So R will be A times A times A times A N times. And then you, what are the vertices of the dot product graph? Is gonna be all the elements in R. You take away the zero element, okay? So the vertices will be all elements of R except the zero element. And the total dot product graph is an undirected symbol graph with this set to be the vertices, and two distinct vertices are adjacent if and only if. Here dot mean the dot product. The normal dot product equals 0. Okay, let me stop for a minute here. Imagine that you take N to be 1. N to be 1. Well, I will talk about that when I define the other one, will be more clear. Okay, so for the time being, you have a commutative ring A, and you take the product of A N times, and you define a ring R, and then the total dot product of R will be undirected symbol graph with a vertex set equal to R star, and two distinct elements are adjacent if the dot product equals 0. Now, what about if we take the 0 divisor of R? Here is your R again. So what about if we take the 0 element? Then we can define the 0 divisor dot graph, and this is the notation. And definitely this will be an induced subgraph of the total dot product graph. What's the difference between the total dot product graph and the zero dot product graph? The difference in the total dot product graph, the vertices will be all the elements in R except 0, where in the 0 divisor dot product graph, the vertices will be all the 0 divisor of R, take away 0. So now I go back to what, early I tried to mention. If you take N equal 1 and you look at the 0 dot product graph of R, then this will be nothing but the classical 0 divisor graph of the ring A, which will be R, because here I'm allowing N to be 1. When N equal 1, then R equal A. So when you're talking about the 0 divisor dot product graph, this is nothing but the classical 0 divisor graph in terms of Anderson and Livingston. Okay. So here, if you want to follow my talk, we have two graphs, total dot product graph and the zero divisor dot product graph. The total dot product graph, the vertices, all the elements in R here except 0, where the zero divisor dot product graph, it will be the zero divisor of R take away 0. And how you connect? Just you do the dot product, the normal dot product, you know, coordinate wise, and you are done. Okay, we move on. Here is the first result. This is, by the way, this work published already in 2015 on the dot product graph, and it appeared in Communication Algebra. In fact, there was a special issue, I think, in honor of, if you heard of Marco Fontana, they make a special volume on, anyway. Okay, so let A be an integral domain, and you take R to be A cross A. So R will be the product of A with itself. Then the total dot product graph is disconnected. Okay? So if R is a product of two integral domain, the total dot product graph is disconnected. And the zero dot product graph is nothing but the classical zero divisor of R. This here, gamma R, this means the classical zero divisor graph of the ring R in terms of Anderson and Livingston. So these two will be the same. So the total dot product graph will be disconnected, where the zero dot product graph will be connected. And here, if A is ring isomorphic to Z2, so here like you have Z2 cross Z2, then the zero dot product graph is complete. And the girth, you know, and let me remind you, this is what we mean with the girth. The girth is defined to be the shortest, the length of the shortest cycle in the graph. And if there is no cycle, then we say that the girth is infinity. So in this case, if A is Z2, which is nothing, you know, this is already known. Why? Because the zero divisor, the zero dot product is the same as the classical zero. So these are known. If A is not ring isomorphic to Z2, then the diameter of the zero dot product will be 2 and the girth will be 4. And again, these two like cheating in a way. Why? Because I mentioned that the zero dot product in this case will be the same as the classical zero divisor graph. And these things are known for the classical zero divisor graph. Okay, now we move. What about if n, because in the previous result, I told you what's going to happen if n equal 2. What about if n is bigger than 2? Okay? Then here is you have a complete classification when the zero dot product graph will be the same as the zero divisor graph. The zero dot product graph of R will be the same as the zero if and only if n equal to A integral domain or R is ring isomorphic to this ring. So this is exactly when the zero divisor dot product is the same as the classical zero divisor of R. It's a complete characterization that A has to be integral domain, N equal to, or R is ring isomorphic to these product of these three rings. Okay. Now let's go back. What about if R is a product of two A cross A, but in this case we have like A is not integral domain. Remember that in the first result and the second, or at the beginning, I consider R to be a product of two rings and A to be integral domain. Here I mentioned that R is A cross A and A is not integral domain. Then what can we say about the total dot product graph of R? Is connected and the diameter will be 3. So if A is not integral domain, then the total dot product will be connected and the diameter will be 3. The zero divisor dot product will be also connected. The zero dot product will not be the same as the zero divisor graph, and the diameter of the zero dot product will be 3. The girth of the zero dot product will be the same as the girth of the total dot product, which is triangle 3. Okay? Again, what do we mean with the girth? The girth is the length of the shortest cycle. If there is no cycle, then the girth will be infinity. Okay? All right. So these are basic properties of the total dot product graph and zero divisor dot product graph. Okay, if you choose A to be a commutative ring with 1, so if you take a product of 3, remember that I was taking like R to be A cross A. What about if I take R to be A cross A cross A cross A 3 times? Then the zero dot product will be connected. If A is not integral domain, then the zero dot product is connected and the diameter is 2. Look, in case number 1, I still have the same ring, is a product of 3 things, A cross A cross A. But if A is integral domain, then the diameter will be 3. If A is not integral domain, then the diameter is 2. And if you take N bigger than 4, then again the zero divisor dot product is connected and the diameter will be 2 again, if N is bigger or equal to 4. Okay? Here is another one. If you take N bigger or equal to 3, like, you know, again, A cross A cross A N times. The only restriction, N bigger or equal to 3, then you conclude that the girth of, which is clear maybe or maybe not, but anyway. Okay, what's added to that? Recently, I have a student, he finished his master thesis with me, and now he went to Germany to finish his PhD. His name Muhammad Abdullah, and he studied the dot product graph. That's the title of the paper, and get accepted, but did not appear yet in International Electrical Journal of Algebra. And his thesis, we studied the unit dot product graph of R. Remember that the first paper was about the total dot product and the zero divisor dot product. So what about if you study the unit dot product of R? And as you expect, maybe I should not give you the definition, maybe from the name, again, I mean, this is maybe smoking. I hope it's not Corona. So from the name unit dot product graph, the vertices will be the set of units of R. So we take the units of the ring R, this R here. And as usual, how you connect two vertices will be connected by an edge if and only if the dot product is 0. Okay? So this is the unit dot product graph of R. Okay, and this is in fact involved a little bit, not fancy, but you have to know some basic number theory to do this kind of construction. We study it over a finite field. Like I let my ring A to be finite field. Like the first case, we took R to be a Galois field with 2 to the n element, and you do the product of this field with itself. Then definitely this will be, I think I mentioned that because this become integral domain. And when integral domain across integral domain, then you will have this from my early result. The 0 is not interesting to me. Here is what new. The unit dot product graph for this ring is this joint union of one Km. Km, oh, you know what Km mean? Complete graph with M vertices. And remember what is M? M is given here to be 2 to the n minus 1. Okay? And that many bipartite complete graph, KMM. So we have a complete description of the unit dot product graph in case of R is a product of two field, Galois field, finite field of characteristic 2. If you have R is a product of two fields of characteristic 2, in fact, they are product of two fields are the same. As you see here, Galois field 2 to the n, Galois field 2 to the n. They are the same field, finite field of characteristic 2. Then we know how this graph look like. It's going to be the joint union of one Km and that many complete bipartite graph. And n here, what is m? M is this number, 2 to the n minus 1. Okay? All right. We move on. What about if we take, remember in the first result, and this is the case maybe always in ring theory even, whenever you have your ring of characteristic 2, many times you have to deal with this case like a special case. For all other, if your ring of characteristic different than 2, maybe you will have a proof, but of characteristic 2, maybe you will have a different proof. And unfortunately, 2 is a prime number. It's the only even prime number, or maybe fortunate, I don't know. Anyway, so if you take a prime number that is not 2, and you look at the Galois field now, with p to the n element, Galois field, that's the notation here. and you cross product the Galois field with itself. Then you have a description. Again, this is not surprising because we know that from the first result, because again, this is integral domain. And we know that the zero dot product. So I'm not gonna mention that. I'm gonna go and mention the unit dot product. Here, what I told you, you need to know some elementary number theory. If 4 is not a factor of m, here is m. M is p to the n minus 1. If 4 is not a factor of that, then the unit dot product graph is disjoint union of that many m over 2 of complete bipartite graph, or the, I'm not sure, yeah, I think complete bipartite. Maybe at the beginning I mentioned bipartite complete, but I think the correct name is complete well, anyway, you get me. Is it yeah, I think bipartite complete graph. You know what that means, KMM. If 4 is a factor of m, then the unit dot product graph is gonna look like union of 2 km and that many kmm. If 4 is a factor of m, then the unit dot product graph of R, the structure will look like that. Okay? And of course, here we also study the total dot product graph in case 4 does not divide m and 4 divide m. Remember, the total dot product graph, the vertices will be the set of all the elements in R taking 0, where the unit dot product graph, the vertices are all the units of R. Okay? And this is here you can read the structure of these things. Okay, and here is an example. I don't know, on the paper, these things, they look fine, but here I have them like, the vertices are not clear. But anyway, you don't have to know the name, but if you take this ring, A, the polynomial ring with coefficient from Z2, and you mod by this ideal generated by x squared plus x plus 1. So this is my ring A, okay? And then you take R to be A cross A. Here is your A. Then here is an example how the unit dot product graph will look like. It will be 2 component. As you see, one is complete, is K3. This is K3. And the other component is K33. This is K33, this component. And this component is K3, complete. Here is another example. If I take A to be Z5, the field with 5 elements, and you take R to be the product, A cross A, then this is how your unit dot product look like. It's gonna be, as you see, 2 components. Each one of them is K4. This is K4, and this is K4, and this one is K44. This is the structure of the unit dot product graph when you take R to be A cross A and A is Z5. These are the examples here. Here is a very nice, which is the proof. I mean, here's the thing. Usually, I'm a mathematician who I like the result more than the proof. I'm not going to discuss it with you. I mean, what I mean, I like it more than the proof. I have to, explain that to me. sometimes they tell you the proof is easy. Well, this is my enjoyment. Whenever, as long, I mean, the proof does not need to be complicated to make the result beautiful. I mean, like here, the proof of that, maybe 2-3 lines. But look at it, it's kind of nice when you look at it. If you take n to be an even integer, Zn cross Zn cross Zn, k times. When k is odd, positive integer, then the unit dot product is completely disconnected. Wow. If you think about it for maybe 5-6 minutes, maybe you discover the proof. But I think we all agree this is not bad. I mean, it's a nice result. That if n is even and k is odd, then the unit dot product is completely disconnected. And that's make you, and when you try to prove it, you see, in fact, why this is the case. All right. And here is the example, like if you take A to be Z8, and I look at the unit dot product graph, it's gonna consist of these two components. Okay. And here is I have an example when A equals Z10, because, I think maybe one result is missing, or maybe I skip it, where, yeah. You remember that at the beginning we study field. Then after that, we consider Zn, like R will be Zn cross Zn cross Zn. And this is done. We know how the unit dot product graph look like in this case. Okay. Here is R is Zn. Yeah, here. Yeah, but this is like a small result. But I think I forgot to add the result about the unit dot product when R is a product of Zn with itself. Anyway, we have, so this has already been done for Zn. But here are examples, Z8, because remember here, I'm not taking field anymore. I'm taking Z8, like Z8 is not a field. So I'm taking Zn, okay? This is how the unit dot product for Z10, then this is how the unit dot product will look like. And if you are interested in these things, I can always send you these favors. Okay, before I finish and I move to the other type of a graph, I like to mention that one thing, there are, there are things you can study on dot product graph, like the dominating number. I did not do that. There is like the genus, is not, to my best knowledge, has not been done yet. Maybe centricity or thickness or, all these graph properties. We only, like here, we studied only diameter, girth, and structure of these graph. But dominating and these things, we did not do it yet. But maybe it can be done, or easily can be done, I don't know. Because, when you know these components, maybe you know what's the dominating number. Or maybe not. Okay, anyway. Another type of a graph is a trace graph. How many minutes left for me? Hello? Hello?
Ayman, you maybe
Yes.
take another 10 minutes and so.
Ayman?
Okay. Okay. Thank you. So everything is work perfect from your side?
Yes, everything is perfect. You may go another 10 minutes
Okay, thank you.
and for 10-minute discussion. Yeah.
10 minutes, I think that will be enough. The other type of a graph is the trace graph. Trace graph, why did I put it with the dot product graph? Because if you talk linear algebra, you have inner vector space. And dot product, in fact, this is how I thought about dot product at the beginning. By teaching linear algebra and talking about dot product. So this is how I come up with the idea of dot product graph. And I hope that these people have the same idea or the same, why did they think about trace graph? Because, you know, trace, also another, you can define another inner what do you call them, in our product vector spaces, you know, whenever you study the inner product, we always teach like, you know, the one for trace and one for dot product and maybe one for polynomial, but I have not seen the polynomial one yet. Maybe somebody will study it. You know how the polynomial will be. Maybe it will be similar, I don't know. And maybe there are other inner, you know, of course there are other. So you can generalize this kind of ideas. So this is one reason why I bought the dot product graph with the trace, because both are, you know, things we do whenever we teach linear algebra, whenever we talk about inner product of vector spaces. So in this paper, they define, of course, here we're only taking the definition, because what we have to be careful. Not all, you know, when we talk about vector space, because unless your things is over a field. Anyway, let R be a commutative ring, and you take Rn by n be the ring of all n by n matrices. And you set this set of vertices, Vn. So you need to know what is Vn. Vn is all the matrices n by n such that there is a B, also n by n matrix, where the trace of AB equals 0. So this is your Vn, okay? So if you let n equal 1, n equal 1, what is V1 will be? The zero divisor of the ring A, right? Sorry, of the ring R. A here is a matrix, okay? So if n is equal 1, V1 will be nothing but the zero divisor of the ring R. Of course, I think maybe I'm missing something here, which is A need to be non-zero matrix. Okay? Yeah, because if we allow zero matrix, then
There must be non-zero.
yeah, non-zero, yeah. So here I'm just, you know, A is non-zero.
Yes.
That should be clear.
It must be here.
Yeah, R, yes. And yeah, anyway, so Vn will be a non-zero matrix in here where this is true. So what is the trace graph? Is undirected symbol graph with vertex set Vn such that two distinct vertices C and D, and the vertices here will be in Vn. Matrices are connected if and only if the trace CD equals 0. Remember that in the dot product, we have the dot product of 2 points to be 0. Here we have trace of a product of the 2 matrices to be 0. This is, and here I'm using my notation because I don't like to write gamma. Don't ask me why. I just write TR. This is for a trace graph. So I apologize for that. So TR graph, this is the trace graph. And this is studied in 2008. So relatively speaking, this is kind of new. And this paper appeared in Acta Math Hungary. And these are the names of, in fact, I know this person. I met him a few times, and I know maybe I saw the other two, but I know the third author of this paper. Okay, what they did there, the diameter of the trace graph is always 2. The girth is always 3. And then they calculated the degree of the vertices in the trace graph. Like the degree of A will be K, and this is of course when R is finite ring. This result is true whether R is finite ring or not, but need to be commutative R. So the diameter of the trace graph of any of the matrix ring over a commutative ring R, n by n is always 2, and the girth is always 3. The only restriction here, n bigger or equal to. So we're avoiding the the 1 here. So 2 by 2, 3 by 3, 4 by 4. These are kind of for a ring R is finite. Well, if your ring is finite, then the trace graph definitely would be a finite graph. So you can talk about the degree of a vertex. If you let the cardinality of R to be K, and this is, I define it here, IA is the ideal of R generated by the entries of A. Remember, A is a vertex in Vn. What I mean a vertex in Vn, that means A is non-zero, and there exists a B in another matrix, B n by n, where the trace of AB equals 0. You know, the set Vn, the one I mentioned earlier. That's your set Vn here. So A is a vertex. Then they gave exactly what's the degree. It's going to be the cardinality of the ring R to the n square over the cardinality of this ideal. And of course, I mean, like quickly, if A contains a unit, one of the entries, then definitely the ideal here will be the whole ring R. So this will be over K here. The interesting thing for, like matrices where the ideal generated by all the entries are not, units or something. I mean, well, even if they are not units, maybe sometime you get them to be the whole thing. Anyway, so this is a nice result, calculating the degree of each vertex. In fact, that was also Professor Shelvam and his colleague. They used that. Sorry?
Sivaham, the other attorney.
Yes, yeah, your co-author. Yeah. Anyway, so you can see how they calculate the degree, and the minimum degree of the total of the trace graph is that. And if R is a field, then the maximum degree of the trace graph is this number. Okay, and then the study, like if you have a finite graph and you put the degrees in a non-increasing order, like you have a graph with k vertices, then you put like D1 greater or equal D2. You can always do that. And then there is something in graph theory, they call it irregularity index. They call by TD. And what's this irregularity index? Is the number of distinct terms in the degree sequence. So if you have a graph and you put the degrees of the vertices in non-increasing order, as I mentioned here, D1, and you're looking at the how many distinct terms can we have? And look, I mean, this is also one of the nice result I call. It does not matter what proof, long or short. Then the irregularity index is 2 if and only if R is a field. Okay, and they gave that the irregularity index of this trace graph is 3 if and only if R is either this ring or this ring. So that means if you have this ring or this ring, and you arrange the degree of the vertices in non-increasing, then the number of distinct terms will be 3 only if your ring R is this ring or this ring. That's beautiful. Okay, and then in 2019, very recent, Professor Shelvam and Sivagama, also in the same journal, they studied the trace graph. And there they calculated like where there are many things, like the dominating number. They took R to be product of Z2 M times. M could be 1, by the way. In fact, the major result was about M equal 1. Then they use result they already proved to get it in general. But if you take R to be Z2 cross Z2 cross Z2, and you find, if you try to calculate, and you know dominating numbers, these are hard problems, then the dominating number of the trace graph will be 3, okay? They prove that the trace graph is never planar, and it's never Eulerian. And of course, you expect how they prove it is not Eulerian. Well, one of their results, they prove that in the trace graph, there always a vertex that has an odd degree. Because if you have a graph and one of the vertices has odd degree, then the graph cannot be Eulerian. And they use that argument to show that the graph cannot be Eulerian. To show it's not planar, they calculated the genus. And I think in some cases, the genus of this graph is bigger or equal to 9, and in other cases, bigger or equal to 4. This is a nice result that the trace graph, every edge in the trace graph lie in a triangle, and every vertex lies on a cycle of length 4. Wow, every edge has to be in a triangle, and every vertex lies on a cycle of length 4. And then this is my last, and I finish. The trace graph of Rn, maybe this is supposed to be n by n, missing. The same thing here, notation, sorry. Your R is that. And you remember the trace graph for matrices. So here I meant n by n. The matrices with, the same thing here, n by n, all of them, n by n, okay? Because we're taking the trace graph of matrices over R. So in this result, the last one, all the n here, this one here is n by n, n by n, n by n. Okay. So this is never planar. Then the trace graph of the matrices n by n over R is a spanning subgraph of an Eulerian graph. That's a nice result. And if R is finite, then the trace graph has a spanning Eulerian subgraph. And all of us know what a spanning subgraph. All of us know it's a subgraph, but you should include all the vertices. But we have a spanning Eulerian subgraph if R is finite. In fact, he used names. This graph here, they call it sub-Eulerian, and this here, they call it super-Eulerian. I just mentioned directly without going through definition. The complement graph, and all of you know what's a complement graph, is always connected of the trace graph n by n. And the last result, if n by n, again, all here also n by n, the trace graph can be decomposed into two planar, you know what a planar subgraph. So it can be decomposed into two planar if and only if n equal 2 and R is Z2. This is a very nice result too, complete answer when this can be decomposed into planar. In fact, the definition in a graph, I think we call it the thickness of the graph, which is the smallest number where a graph can be decomposed into planar subgraphs. Well, he has another paper, the same author, Sivagama and Shelvam, and I don't have time to talk about their other papers. Maybe, in fact, I'm not sure if it appeared or not. Did it appear yet?
What?
Your second paper on trace, did it
The same
appear?
name.
Oh, okay.
Yeah, the same student.
Okay.
SCPT Journal of Mathematics and Statistics.
Okay. So here are the references. This is for the trace graph. This is the classical zero divisor graph. No, this is the classical. Here, Anderson and Livingston. These are the two papers on dot product. Well, no, this is on dot product. And this one, the recent one. And these are the two papers I have for Professor Sivagama and Shelvam on trace graph. So for a student, maybe there are more can be done on dot product and the trace graph. These are, relatively talking, are a new graph, and maybe there is something there to investigate. Okay, thank you very much.
Thank you, sir. Thank you, Professor, for your clear presentation. With your permission, may I ask participants to clarify their doubts?
I wanted to have one question.